Today we're very happy to have Dr. Donghan Yeom. You can see his, except the Yeom, Donghan is exactly the same as in Mandarin. So Dr. Yeom did his studies at KAIST in Daejeon, in Korea, receiving his PhD in 2011, after which he went to Sogang University in Seoul at this Center of Quantum Spacetime. Pretty fancy name. And spent a postdoc term there, and afterwards he spent some time at YTP, the Cullen Institute in Kyoto, and since last year he arrived here in Taiwan at LeCosPA, and the boss is here to monitor the whole thing, or maybe learn the subject. I don't know. Anyways, as far as I can tell, Donghan is infatuated with information loss problem for black holes and black hole evaporation. And this is certainly a very intriguing, fascinating, and more or less fundamental subject. So he's going to tell us. I asked him to be pedagogical, so we'll see how he does that. Okay, the floor is yours.
Yes, thank you very much. Can you hear me?
Yep.
Yes, so I'm very happy to meet you and to have the opportunity to talk about this issue, information loss, and its controversy. And today, if you, especially for students, if you have any questions, then please interrupt and please give me any questions. So let me start. Before I start from the information loss problem, let me comment the general relativity and quantum mechanics. So the question is, can you make a constant theory with general relativity and quantum mechanics? That is some fundamental question. So maybe you will see this Einstein equation. This is the Prescott equation of motion. And you will see the Schrödinger equation, but you will see some head rotations. So this means that this is a kind of operator relations, and should have to quantize and should solve the equation, Schrödinger equation and wave functions. Then this is related to, so if we quantize gravity and everything at the same time, and if we make a quantum theory of gravity, then this is related to quantize the matter. This means that if we solve the psi in full quantized wave function of all matter field, then psi should be a functional of matter. And so maybe I don't know much about the quantum gravity, but this is really difficult. Everybody knows that this is really difficult. But today I will discuss that it is even worse. So not really difficult, but also brings very subtle problems. One of the such a subtle problem is the information loss problem in black hole physics. So let's go. And what is the information loss problem? And let me say why is it a problem? So let me briefly comment about. So I titled everything about general relativity. Of course, it is not everything, but let me very compactly summarize important points. So space-time is one doctrine of general relativity is that space-time is a Riemannian manifold, a geometrical object, and should satisfy this equation. GAB is A pi TAB, so-called Einstein equation. So the first doctrine is that space-time is determined by this equation, field equation. And the second doctrine is that we are, so every observers are geodesics on this manifold, satisfying special relativity locally. So, relating these two things. So one is about Einstein's field equation, and the other is about so-called geodesic equation. So relating two things, maybe we can remind these two things. So one notion is world line. So every observer, we are forming time-like or null curves on the space-time. So I'll say about the time-like. And the other point is that the causal structure. For each point, the observer cannot move faster than the speed of light and should be located inside the right term. So So every observer cannot move faster than the speed of light and should be located 45-degree curve. Maybe we know in special relativity there is a light cone. So we should locate every time in light cone. So I draw this arrow. Let's say that this is the world line. So we are on line that satisfies geodesic equation. Then approximately the horizontal direction is a space direction. So r equals 1 or r equals 2 or r equals infinity. And the y-axis is time direction, temporal direction. So time flows from bottom to up direction. So usually this is the world line. And for each point, the tangent vector, velocity vector should be located inside the light cone. This means that the velocity is less than the speed of light. For every tangential point, it should be located inside the light cone. So I think that that's all about general relativity and all needs about my presentation. So, and let's just say about everything about black holes. To discuss about information loss, I have to say about something about black holes. General relativity allows solutions, so-called black holes. For example, this metric. This is the most famous black hole solution, so-called Schwarzschild solution. And if you carefully see the behaviors of this metric, then there are some important. One is r equals to infinity. So r is the library speaking distance from center. So if r goes to infinity, then we becomes very far from some massive object. So this means that r equals to infinity is somehow flat space. So people say that it is a future infinity. And the other point is r equals 0. So if r goes to 0, then this metric becomes singular and singular. And not only metric, but also some curvature quantities also diverges in r equals 0. So r equals 0 is really physically meaningful singularity. So there are two things. And after a very simple calculation, we can check that future infinity is a null direction. And the singularity, r equals 0 singularity is some space-like hypersurface. So let's draw one. So singularity, r equals 0 is some space-like surface. So it should be outside the right point. And future infinity is the null surface like this way. Then in between the singularity and the future infinity, maybe we can say something, so-called the event horizon. So event horizon is defined by this causal boundary between future infinity and singularity. So I said that we cannot move faster than the speed of light. So if we draw the event horizon this way, then this becomes the causal boundary between singularity and future infinity. So at once one observer crosses the event horizon, then this observer cannot move to future infinity forever because it already passed, it already crossed the causal boundary, so-called event horizon. However, if one observer is always outside, so if one observer always do not touch the event horizon, then this observer can go to future infinity. So this observer will be happy and will not die inside the black hole and singularity. So the first observer who crosses the event horizon is called by infalling observer. So falls into the black hole and eventually touch the singularity. While the second observer is so-called asymptotic observer and who can stay infinitely as outside the black hole. So up to here, do you have any questions? Yes. So I think this is quite trivial. So to discuss the black hole information loss problem, I have to further some advanced topics around the 1970s. So black holes have thermodynamic properties. This was observed by Harding, Carter, Hawking, and Hawking. So in terms of years, the first one is Hawking's 1971 paper, and Hawking could calculate the variation of area always increases greater than 0. He had to assume some metal conditions, but within very reasonable condition, for any process around the black hole area should increase for every cases. I mean, the area of the event horizon should increase for every process. This was first observed, and 2 years later, Adin, Kato, and Hawking derived this formula. So here, M is the mass of the black hole, and A is the area of the event horizon, and J is the angular momentum. So if we vary slightly the mass of the black hole slightly, then area should vary this way, and angular momentum can vary. But there are some coefficients of yours. So kappa is called by the surface gravity that is defined on the horizon, and omega is also some working term, corresponding angular momentum. So we are very tempted to interpret this formula as TE equals TDS minus PD group, the so-called thermodynamic relations. However, it was very unclear what is the temperature and what is the entropy. So anyway, M is the energy, so TE is okay, but how can you interpret this kappa dA term as a TDS-like term? So T is temperature and S is entropy. It was entirely unclear. But surprisingly, in 1975, Hawking derived this formula. So a black hole emits particles by a Planck distribution with the Hawking temperature. So what Hawking calculated is the expectation value of number of particles with a given energy omega. So for a given energy omega, he calculated the distribution of the number of particles as the expectation value. And the result looks like Planck distribution, where this part is exponential omega over t, and omega is energy of particles. And this term should correspond to the temperature of the Planck distribution. And temperature, so this means that temperature should be kappa over 2 pi. So if T is kappa over 2 pi, then we can read the entropy relation. Since black hole emits particles and it becomes a thermal distribution, then we can say really something about thermal entropy, and the corresponding coefficient is 4, 1 over 4, because this is 8 pi and this is 2 pi. So the entropy should be 8 over 4. So this was
can you explain the angular momentum part?
Yes. So this can have some analogous about PDV term, so-called working terms. And I couldn't exactly remember what is the definition of omega, but the only thing what I can say is it is related to working term and well-defined classical term.
But does it mean that this is a differential relation, but in terms of the integral relation, because there's a minus sign there.
Yes. So it's up to our definitions.
Huh?
So it's up to our definitions.
But is it absolutely negative? I'm not absolutely.
No.
It can be negative.
No, yeah, right.
But doesn't that cause a problem?
So I should carefully check about the definition of omega, so whether it is positive or negative. But I think it's up to our definitions.
Okay.
Yes. So the important thing is that we could derive that entropy is A over 4, and we calculated factor 4 exactly. And you can see that year of investigation was 1974, but Hawking calculated this in 1975. So Bekenstein first conjectured that black hole area and event horizon area should be proportional to the thermal entropy. But at that time, Bekenstein could not calculate exactly proportional constant. But after the investigation of the Hawking radiation, we now calculate exactly that it is 1 over 4. So what is the implication of the black hole thermodynamics? Black hole emits particles. So what happens? The result is black hole evaporation. So black hole is a thermal object. So black hole becomes a black body. So it will radiate black body radiation. Then according to Stefan Boltzmann law, the DMD, so mass change ratio, should proportional to area as well as the T force. Then after simple calculation, it proportional to -1 over m square. And then as time goes on, temperature increases and black hole becomes smaller and smaller, and eventually it will disappear. So it will radiate something. So such radiations are called by Hawking radiation, and because of the Hawking radiation, black hole size will be smaller and smaller. So as the black hole size becomes smaller and smaller and smaller, it will approach so-called the Planck scale. So if length becomes the order of Planck scale, then we cannot trust the general relativity or quantum mechanics. So there is no principle. But so maybe in the final stage there can be some Planck scale effects. But usually people may believe that the Planck scale effect is just order 1 compared to very large size of black holes. So if we neglect about such a Planck scale effect, then the only remaining thing is the information about Hawking radiation, and we can calculate the Hawking temperature and back reaction to Hawking radiation, and usually this only depends on macroscopic parameters. So the evaporation mainly depends on mass, charge, and angular momentum, such as macroscopic classical parameters. This means that maybe we may lose some quantum numbers and so on. Then can we recover information except mass, charge, and angular momentum? So this is the origin of the information problem. But shortly, let me say what is the information. What do you mean by the information? So let me shortly discuss about what is information. So information means that a less probable event or state has a larger information. So maybe we define this way. So I is a certain state or a certain event, and P is a probability of such a state. Then Claude Shannon, the one father of information theory, defined the information by this formula, minus root pi. So and since pi, as pi becomes smaller and smaller, information increases. So a less probable event or state has larger information. And Shannon defined the entropy like this way. So entropy is the expectation value of information. So as is defined by expectation. And so we sum over all states weighting probability, then it is expectation value. And we can also prove that the entropy is the capacity of information. What is the capacity? For example, I have one memory, and this memory has, for example, 2 gigabytes capacity. This is the entropy of this memory. So we cannot store more information than this capacity. I cannot store 3 gigabyte information to my 2 gigabyte memory. So this is the notion of capacity of information. Then what is something to do with our physical entropy? So in quantum mechanics, we introduce the wave function, and we can introduce the density matrix. So from this density matrix, we can define so-called the notion of the von Neumann entropy. And von Neumann entropy can be changed into this form, pi log I. So this is exactly the same as Shannon's entropy formula. So von Neumann entropy is really the same one with the information theoretical entropy. And we can also say something about the thermal entropy. So in the thermal equilibrium, we expect that every PIs are randomly mixed. So every PIs becomes 1 over n, where n is the number of accessible states. So if we change it to 1 over n, then we can simplify such a von Neumann entropy, and we obtain entropy as a log n, where n is the number of states. So this means that this is in fact the summary in the summary equilibrium, the entropy becomes log n, and this is indeed the maximum possible value of the entropy. So this is the maximum entropy, and sometimes it is called by Boltzmann entropy. So Boltzmann entropy is very useful in any thermodynamic context. So one special case of the maximum value of von Neumann entropy is Boltzmann entropy, and the von Neumann entropy can be interpreted by the information theoretical sense. So this is a basic definition of information, and let me say more details about what is going on in black hole physics. So, what is the conservation of information in black hole dynamics? Let us assume that we consider this system. So, first step, I prepare some closed system with the total number of states n, capital N. So, n will be conserved. And I divide by two subsystems. And initially, the total information is, for example, I0, because this is the capacity of this system, so I can write some information up to log n. So let me say that initially there was such kind of amount of information, and initially it was concentrated at A. So P has no information, and A contains every information initially. And the question is, now I want to move particles from A to B by some way, either Hawking radiation or any method. Then, in this situation, will the amount of total information conserved in the end or not? And how to define the information for this situation to say something about the information conservation? So, information theorists can especially introduce a very useful notion of information in this when the information is transferred from system A to B. This is the notion of the mutual information. So mutual information, so I, P colon A is defined by SP minus HP by A, where SP is previously I defined the maximum entropy, so Boltzmann entropy. So SB is Boltzmann entropy, and SP bar A is so-called the entanglement entropy. So for the density matrix law, we trace out the degree of freedom of A. Then let's define that as rho A. Then using the rho A, we can also write down the von Neumann entropy for this subsystem B. This is the definition of the entanglement entropy P by A. So SB is a very naive concept. We completely ignore the A part and just naively count the number of states for SB. And SP bar is rather more somehow detailed concept, because we carefully consider about A and use the microstate countings. So sometimes people say that SB is the coarse-grained entropy, and sometimes people say that SP bar A is the fine-grained entropy. And the difference between coarse-grained entropy and fine-grained entropy corresponds to the transferred information from A to B. So this is the definition of the mutual information. So this is my hard disk in my desktop. So what is the information from this figure? So first, total capacity is 116 gigabyte. This is the naively calculated total capacity that I can use. But in practice, I cannot use the total capacity because I already used it. So the really writable capacity, the really usable capacity is 28.6 gigabyte. Then the difference between total capacity and writable capacity is the information. So I used them, and I write the information using this portion. So this corresponds to the information, and information is difference between total capacity and writable capacity. So SB is a naively calculated total information capacity for system B, and SP bar A is more carefully calculated really writable capacity. So in this sense, we may intuitively agree with this. So for unitary processes, if information is conserved, then some relations are specified. But let's go to the next slide, and let's see what is going on in terms of pictures. So x-axis is entropy of system B. So x-axis is SB. So if I plot SB, then it is the exact diagonal line where SB is log n. So the Boltzmann entropy counted by outside of the black hole. So this is log n. So initially it was exactly 0 because initially there was nothing outside the black hole. And as time goes on, in the end, SB becomes the maximum value because black hole completely evaporates and disappears.
So what's M?
M is the number of states for outside the black hole. And the total system is conserved. So total number of states are conserved. So SA copy. So the total entropy should be conserved as a constant. Then the difference between SB and SA copy is the entropy of the black hole. So entropy of the black hole should decrease. So here is the comparative evaporation, and here is the starting point. So from initial point to here, it should monotonically decrease and completely disappear at this point. And SA is the black hole.
Excuse me, why initial entropy is equal to the total information? I mean,
initially, we assume that there is nothing outside the black hole. So SB, outside entropy, is zero.
yes, but SA is the maximum value of information initial state.
Yeah, right, right.
But I mean, the total information can be smaller than SA.
Right.
Initial value of SA. Why we choose this special case?
So this is not information, but SA
This is
is
capacity, right?
black hole entropy.
Yes, so roughly the capacity of A.
Yeah, right, right, right.
Then initially capacity of A is this max.
Yeah, right, right.
And capacity of A is zero. Capacity of B is zero. And now total information is same as the initial value of total capacity of A.
In fact, this is not the total information, but somehow transferred information, mutual information. So information detected by outside of zero. So initially it was zero, and as time goes on, it
Yes,
increases.
but this means, I mean, initially, information of SA is full.
Yeah, right, right.
Why we assume such kind of case?
So why do we assume that every information was in black hole?
I mean, why all capacity is occupied in initial stage?
Why all capacity is low?
Yeah.
Because we assumed that it was a closed system. So for simplicity, we take it.
Yes. I mean, for example, we can consider the case where there are no information. Even initial state we don't have information. Then nothing happens. I mean, this means initial capacity is different from the total information, usually, generally.
Maybe, yeah.
But seeing this figure, then the information is same as the initial capacity of A.
Yes.
Why do you assume such kind of case?
So one is that maybe we can assume that way, and yes, one is that we can assume and we can simplify the things. I think so. Yes. So let me go further. So this is a black hole entropy curve, and what is the second question is what is the entanglement entropy? So usually it depends on the details of the black hole dynamics, but in 1993, Don Page wrote a very interesting paper, and for some pure and random system, for any system, if the number of states increases more and more, then the entanglement entropy should behave like this relation. So because of this relation, we can very easily calculate the distribution of entanglement entropy. So according to this paper, the maximum of entanglement entropy appears around this halfway point. And before the halfway point, the entanglement increases, and at this point,